Hello, this is Mrs. Nearing, and in this video we're going to talk through the steps in calculating the pH of a weak acid as you titrate it with a strong base. So we're looking at this kind of scenario over here in the upper right hand corner where you are adding a strong base to a weak acid, and we're going to look at the pH at three particular points that are important. And point 1 is before you've added any base. And then point 2 is where you're somewhere along this initial part of the curve where it's relatively flat. And then point 3 is going to be during the steep vertical region. And the midway point of that steep vertical region we call the equivalence point. That's basically the end point of your reaction where you've used up all the stuff that was in your beaker, which in this case is my weak acid. And these are just three very important points to know how to calculate the pH of. So we're going to walk through a specific example to try and figure that out. So we're starting out here at point 1. We're looking at, this is our weak acid before we've added any base to it. So I always kind of break these steps down into two different kind of mental thought processes. So step 1, I'm going to ask myself, what's in my beaker? And then step 2, I'm going to ask myself, what is the equilibrium reaction here? And I'm going to use that equilibrium reaction to find the pH. So step 1, what's in my beaker? For this one, that's easy. It's just 0.1 molar HNO2. I haven't added anything else to it, so that's very straightforward. We know that HO2 is an acid. We might recognize that because it starts with an H in the front. Also, they give us a Ka value for it, so that's a big hint. And we can see that's a weak acid because its Ka value is less than 1. All right, so we've got a weak acid in my beaker. So when we have a weak acid, what does it do? It dissociates into ions, and we can set up an ice chart to figure out how many ions it makes. So I know that I start out with 0.1 molar of my acid. I have none of this in my beaker to begin with. I'm going to use up some of my acid and turn it into ions. My K value is pretty small, so it's 10 to the negative 4, so X is going to be pretty small. So when I go here and plug it into my K expression, I have X times X on the top, that's X squared. And then 0.1 minus X, I'm going to assume that since X is so small, 0.1 minus X is just going to be the same as 0.1. So here's my K expression, and I know the value of Ka, it's 4.5 times 10 to the negative 4. When I solve for X here, that gives me my hydrogen ion concentration, which in this case is 0.0067 molar. And if I take the negative log of that, it will give me 2.17. So that's my initial pH of my weak acid. Seems reasonable. It's an acid. The pH is below 7. Okay, so now let's take a look at step 2. This is where you've added some sodium hydroxide to my weak acid. So step 1, like we mentioned before, is to figure out what is in my beaker. So I no longer have pure weak acid. Now I have added some base to it. Specifically, I've added 40 mL of 0.1 molar NaOH. Notice that this volume is important because since I've added 40 mL to my original 100 mL, my volume is now 140 mL. And that's going to make a difference later on because we'll find that the molarity of everything, all my ions and molecules, is going to get diluted because my volume just got larger. And remember, molarity is moles per liter. So we'll come back to that in a minute. And, okay, what's in my beaker? I've added some hydroxides. Okay. I'm going to ignore the sodiums for right now because they are spectators, but we should recognize they're there in the solution. These hydroxides, when you put them in here with the HA, they're not going to hang out there by themselves. They are going to want to react. So what happens when you add a strong base, hydroxide ions, to a weak acid, those hydroxide ions are going to come in, they're going to grab a hydrogen from my weak acid, forming water, and leaving behind A minus, the conjugate base. So when these hydroxides come in there, they aren't going to stay as hydroxides. They're going to turn into H2O, and they're going to do that by using up one of those H's. So let's draw a few of these here. So all my OHs get turned into H2O, and my HAs get turned into A minus. So one thing you want to stop and recognize at this point is that you now have a mix of HA and A minus. You have a weak acid and its conjugate base. So that means you have a buffer. So that's an important thing to realize. There's two ways in which you can make a buffer. You could just mix together a weak acid and a conjugate base, okay? Or you could start with pure weak acid, add some strong base to it, and therefore generate some of the conjugate base, and then voila, you have a buffer again. And you'll notice over here, if we go back to this graph, remember we're here in this zone in the middle, and this is the buffer zone. This is the buffer region. So in this region, you have a mix of HA and A minus, as opposed to here, initially, you only had pure HA. So right here in the middle, you've got HA and A minus, so it's a buffer, and we'll notice that the pH is staying relatively constant in that buffer region, which makes sense because we say that buffers are solutions that resist change in pH. Okay, so here we are with we've got a buffer, but we have to find the exact pH of our buffer, we have to quantify how many HAs and how many A minuses we actually have in our solution. And this is going to be a stoichiometry problem. Really what it is, it's a limiting excess stoichiometry problem. We have to figure out how many moles of HA were in my beaker and how many moles of hydroxide were added, so we can figure out how much got used up and what's left over. So if we work our way through this here, my hydroxide, let's look at that one first. I added 0.04, let's see, yep, 0.04 liters of 0.1 molar hydroxide ions. So that means I had 0.0040 moles of hydroxide. And I represent it in this picture by drawing 4 of them. Okay, now let's look at our HA. We had 0.1 liters of 0.1 molar. So we had 0.010 moles of HA. I represent that over here by drawing 10 HA molecules. And what happens, every OH that you add uses up an HA and turns it into A minus. So I'm going to use a different color to represent that change. So we saw in this picture, all of my hydroxides get used up. And every hydroxide that gets used up uses it up by reacting with an HA. So notice how I added 4 hydroxides. My 4 hydroxides all vanish and turn into water. And then 4 of my HAs vanish and they turn into A minus. So I'm using up all 4 OHs, I'm using up 4 of my HAs, and I am making 4 A minuses. So what's left over? Well, my OHs all get used up, so I've got no OHs floating around in my solution. I still have 0.0060 moles of HA, so notice how I have 6 HA molecules still in here, and I've now generated 0.004 moles of A minus. I also made some waters, but I'm going to ignore that because there's lots of waters around, and that doesn't really make a big difference. Okay, so if we think about what's in my beaker, it's a buffer. It's a buffer with a volume of 140 mils, and it contains 0.0060 moles of HA, and it contains 0.004 moles of A minus. So I've just done all this work, and I still have not figured out the pH yet, right? I'm still on step 1, just figuring out what is in my beaker. So now let's try and use that to figure out what the pH of this solution is. So step 2, to find the pH, you're going to figure out what is my equilibrium. So if we think about what's in the beaker, remember we said we've got HA, A minus, and there's water as well. So the equilibrium at hand here is HA dissociates to make H plus and A minus. Remember, whenever we have a buffer, that means we basically have a reactant and a product in one of these equilibrium reactions. Notice how the reaction here is the exact same as the reaction that I wrote up here, right? So HA dissociates to make H plus, A minus. Although here I use the actual symbols. Sorry, I kind of went into my shorthand here. So I'm going to set up an ice chart. And in my ice chart, as opposed to in part 1, we just had pure reactant. Now, since we have a buffer, that means I have a mix of reactant and product. So instead of being 0.1 molar my acid, I have 0.006 moles acid divided by 0.14 liters. So remember, in your ice charts, all your values should be in molarity. So I have to take my moles and divide it by my new volume. This is 0, and I've got 0.0040 moles divided by 0.14 liters. And then I just go through and do my normal ice chart thing. So you end up with this being 0.043 molar, and then this is X, and this is, I think, 0.029 molar. All right, and then I'm going to take these values and plug them into the same K expression that I used right up here. So I'm going to have my Ka is going to equal my product, so that's X times 0.029 divided by my reactants, 0.043, and that's going to be equal to my Ka value, which was given earlier. And then I'm going to go through and solve for X, and X will give me the hydrogen ion concentration, and I didn't write that down what that was, but if I take the negative log of the number that I calculated, I should get 3.17. That is going to be my pH. Okay, so another interesting thing to note is that if you go through and you take the negative log of the Ka, that gives you the pKa. And if you stop and do that right now for this number, you will find that the pKa is 3.35. So you should notice that when you have a buffer, the pH of your buffer is going to be close to the pKa of the weak acid component in your buffer. And when, if you were to stop at exactly halfway to equivalence, like if you used up exactly half of your HA and turned it into A minus, you would find that the math works out so that the pH equals pKa. So this happens at the half equivalence point. So let's stop and point that out on this graph up here. If we look back at our graph, that would be like right here in the middle. So halfway from the beginning to the equivalence point in terms of how volume of base that we've added. All right, so that was the tricky one. Okay, was doing the buffer. So now let's look at the third point here at equivalence. Okay, so calculating new pH at equivalence when you've added 100 ml of 0.1 molar NaOH to 100 ml of 0.1 molar HNO2. So I added another, this is not going to be to scale, but I added another 100 mils of 0.1 molar NaOH. So what we should notice is that the total volume is now 200 mils. That'll be important because we've diluted everything. And now what's happened is, so first step is, what's in the beaker. So the volume's 200 mils. And we saw this reaction happening. So we're adding hydroxides to my weak acid. The hydroxides are going to take a hydrogen, forming water and leaving behind the conjugate base. And we can go through and do this mole calculation like we did earlier, and we'll find that for both of them, I'm adding 100 mils of 0.1 molar. So I have 0.01 moles of hydroxide, and I've got 0.01 moles of HA. What that means is, notice how we don't have any excess reactant, so everything is going to get used up. and turned into product. So what do we have at equivalence? We've got no hydroxide, we've got no HA, and we just have pure A minus. Whoops, there must be a 0 there. Okay, so I have 0.010 moles of A minus. That's my NO2 minus ion. So all of my acid has been turned into the conjugate base. I won't rewrite all of these, but you get the idea. Okay, so these have been all used up. All you have in the beaker is the conjugate base. I guess I will draw all of them. Okay, there you go. So remember that this has a new volume. So if we're trying to figure out the molarity of your conjugate base, it's 0.1 moles. Just like we had 0.1 moles of acid to begin with, but now the volume is twice as large. So it's in a 200 ml solution. So you will find that the molarity is half that is what your acid started. So you started out with 0.1 molar pure acid. At the equivalence point, in this case, you end up with 0.05 molar conjugate base. Okay, so now that we've figured out what's in my beaker, let's set up the equilibrium and find the pH. The important point here, so now here's really key, is you cannot use this equation up here that we were using earlier, okay? Because we no longer have any HA in our beaker. So what's in our beaker? We've just got A minus, and we've got water, and we've got a bunch of spectator ions. So when we're writing out the equilibrium that's occurring, we have to think about what A minus is doing in water. And we know that A minus is the conjugate base of HA, so it's going to be a hydrogen taker. So it is going to take a hydrogen from water, making HA and the hydroxide ion. And we can set up an ice chart for this. When we write a K expression for it, it's going to be HA times OH minus over A minus. And we should notice that this is actually a KB expression, not a Ka expression. So did anyone give us the value of KB? Doesn't look like it. The problem only gave us a Ka value. So how am I supposed to handle that? Well, if you have a weak acid and its conjugate base, the Ka of your acid, that would be HNO2, times the Kb of the conjugate base, which would be NO2 minus, is going to equal Kw, which is on your equation sheet. It's 10 to the negative 14. So we can find Kb by taking Kw divided by Ka. Okay, and then, so let's plug in some numbers and solve this. So I know this is 0.05 molar. I ignore liquid water. These are starting out at 0 because it's not a buffer anymore. It's just pure weak base. This is going to get used up. This is going to get made. End up with 0.05 minus x, and this is x, and this is x. So we plug this in. X squared divided by 0.05 equals Kb, which when I do this math right here, I should find that my Kb is 2.2 times 10 to the negative 11th. Notice my K is sufficiently small that I can assume 0.05 minus x is just 0.05. When I go through and I solve for x, it's going to give me 1 times 10 to the negative 6 molarity. Remember to stop and look back at your reaction and say, oh yeah, this is actually my hydroxide ion concentration. So for this one, when I take the log of it, it's not giving me pH, it's giving me the POH. So the POH is 5.98. When I subtract 15 and 5.98, I will get the pH, which is 8.03. So to overview here, initially in this graph, we have a pure weak acid, and we're going to use Ka, we're going to use an ice chart to solve for pH. In the middle here, you've got a buffer region, so you're going to have to go through and do your 2 steps. One, you're going to have to figure out, do a little stoichiometry to figure out how much HA and A minus you actually have in your solution. Then you're still going to use this Ka expression and the ice chart to figure out pH. The only difference here, when you're in the buffer region, when you're setting up your ice chart, you're going to have 2 initial values in that first row. If it's pure weak acid or pure weak base, you're only going to have a reactant value. But for a buffer, you're going to have a reactant value and a product value. And then going over here to equivalence, at equivalence, you're going to have pure weak base, so it's going to be all A minus. So when you do the calculation here, you're going to use a KB instead of the KA, but you're still going to set up your ice chart and do your normal calculation.